Please let us welcome Dr. Daniel García-Castellanos,
who's visiting us for 3 months at the Institute, thanks to the mobility program paid for by the Ministry of Education, I think.
Yes.
Daniel works in surface processes. His work has mainly been in the efforts of constructing mathematical models that link the processes or physical processes of the surface of the Earth with the dynamics of plate tectonics. Pretty complicated stuff, but he does it quite successfully. Daniel completed his PhD in 1998 at the University of Barcelona in physics. And after that, he took up a postdoc at the Vrije Universiteit in Amsterdam, where he worked for about 5 years. That's good. And then, and after that, he went on to work at the Spanish Research Council, where he's been ever since. And must be very happy there. Must be looking after you.
It is, indeed.
So thank you very much for coming, Daniel, and please let us enjoy your talk.
Thank you, John. Thank you. I have to thank a lot of people, not just John Johnson, for the opportunity of coming here and getting to know your institute and learning a lot. And I hope I can reward that during the coming weeks and also with this presentation. But I specifically want to thank David Uliczny. I'm sorry I have to read the names because otherwise it's too risky. And of course, John Johnson, Greg Fludnik, Professor Edward Petrovsky, of course, is giving me some references. And I think I said everyone. And Alice Spitzak, of course. Thank you for the fun we are having, because it's not about just learning, but we are having lots of fun. And I'm very impressed of how well organized are this visiting scheme. So, yeah, wanted to start saying that the scope of the presentation is slightly changed, and this is thanks to David, because a few days ago he was telling me about the geological history of the place where Prague is sitting on, this incised river network into this sedimentary basin of marine sediments, and this stayed in my brain. I didn't know anything about the geological history of here, but then he lent me his bicycle, and I had the duty to come and cycle from home to the institute by bike. And that really highlights very much the importance of the topographic relief of Prague. And then I thought that you probably guys are very interested in seeing a bit more about one of the aspects of what was initially the plan for my talk, which is the incision of sedimentary basins upon capture or drainage openings, how sedimentary basins are cut down by river networks. And anyway, I will do that by showing a series of models that are source-to-sink models of surface processes linked to deep geodynamic or tectonic processes. And the aim is to see how the two scales interact, surface and deeper stuff. The open questions. Yeah, the open questions, the broad open questions that I will address, therefore, are, as usually in landscape evolution modeling, can we quantify the evolution of landscape? Can we predict how river networks transport sediment and insights into the landscape? And is there anything as topographic steady state during the development of this? And at what speed do the transient landscapes occur when some external factor, tectonic or geodynamic, is disrupting a topographic steady state? So at what speed is topography changing in the end? That's the overarching question. And this is an outline of the presentation. So I will first show some fundamentals on how the models that I will show. Sorry, it used to work fine. Here.
Okay, what's that?
No, the light is just not going.
Oh, sorry.
So the mathematical approaches I will show first. Some fundamentals of how do I approach each of the mechanisms involved. Then I will show some examples about the opening of the drainage from closed drainage to open drainage in the northern half of Iberia. And I hope I have time to talk a little bit about what I think is the next steps in understanding landscape evolution and how can we benefit from a different process, which are outburst floods sourced at overtopping lakes. All right. That's okay, no, don't worry. Don't worry. I'm fine. Yes, it works for the incident. All right, so the models I will show are these two. TISC is a pseudo 3D model that the name stands for Tectonic Deformation, Isostatic, Surface Processes and Climate. And Tau is just a pseudo 2D version of the same thing. There are both models that are written in C or Linux, and they use this old-fashioned version of GNT for the graphic output. They are open source and they are available at GitHub, and they are non-parallel, which means that if you need lots of resolution, they might be a bit slow and go into the day-long time for the runs. Okay, for the tectonic deformation, I use a very simple approach, which is just predefining, prescribing the shape of faults and the velocity at which they move. And based on that, you produce topography. And based on this stacking of piling up units, then you can calculate the load. And from that, you go to the next step, which is calculating the flexural isostatic response. So you have the load, you can solve this equation, and you can calculate how much the lithospheric plate bends and sinks under the weight of those loads. You can use different rheological models for that calculation. And then you have to play with the value of the elastic thickness of the plate, which usually in continental areas is mostly concentrated between 15 and 30 kilometers. But it might get farther. And this is what controls the width of your foreland basin, if you are modeling a foreland basin, as in this cartoon example. And then we go to the surface process itself. The way to approach or to mathematically calculate the incision rates of rivers are several, are more than one. I show here these two examples, the most common ones. One is the shear stress approach, in which erosion rates in the riverbed are assumed to be controlled or proportional to the riverbed shear stress of the water flow. And another possibility is to approach it by the stream unit power, which would be the work exerted by the water flow at the bottom of the water layer. They have different, of course, different implications, but both of them, okay, well, before I forget, there are two limitations in these relationships, is that these constants of proportionality in both models have a huge uncertainty in their values. They are very difficult to measure in natural scenarios of river incision, and therefore there is no good knowledge as to what values should we put for a given region, based, for instance, on lithology or fracturation of the rock that is going to be incised by the river, etc., etc. So keep that in mind for the end of the talk. There is a big uncertainty in those. Regardless of what of those models you choose, you end up with some sort of stream power law that you might be familiar with, in which erosion rates can be described as a power law of water discharge and slope. Sometimes you see, instead of water discharge, you see area as a proxy for the amount of water that the river is bringing down the channel. But this is not enough to have a source-to-sink model, because source-to-sink models are models that follow what happens from the erosion in the mountain ranges to the sinks in the sedimentary basins. So to reproduce where and how fast sediment is accumulated in the basins, you need to limit the amount of transport that the river can exert. So what you do is you simply put a limit, and when the water is carrying more sediment than what it can actually transport, then it deposits and it sediments in the bottom. All right, so you put this into a discretized topography. So what we do is we discretize in a rectangular grid the topography, and we add all these mechanisms, tectonic deformation and incision and transport and isostacy, to keep track of how this topography is evolving through time. And that includes also the possibility of forming lakes in topographic minima. That's crucial for the story that I will tell later, is that you can actually explicitly account for...
Oh yeah, sorry, that was me.
You can explicitly account for the formation of these endorheic lakes, which evaporate the water that is exposed to the surface in topographic minimum. Okay. No,
Come on.
no worries. Okay, let me show first example about how the surface process model works. This is a drainage capture, and you can see two identical models. This is a river flowing basically flat in a high plateau towards the left, and this will be captured. It's a drainage fluvial capture of one of the streams that is eroding the southern flank, which is a steep southern flank that is flowing to location which is near sea level. So I will play it again. You see these two identical captures. One of them is going faster than the other, and there is only one parameter that is changing between the two. I let you guess what it could be. The lithology of both are the same, the erodibility are the same, the amount of precipitation drop on both surfaces is exactly the same. The only difference between the two is the porosity, is the permeability between the two models. In this one, the substrate, the rock is not permeable, so there is no underground flow. And in this one, there is. So paradoxically, even if in the right model, in the model to the right, there is part of the water that is disappearing from the surface and is infiltrating into the underground, and is actually not eroding. Therefore, it's not eroding because I don't produce any underground erosion. Even in spite of that, the capture happens much faster in this model to the right. And this is because part of the initial rivers, part of the water that was initially draining from the right to the left is diverted to the underground and is helping this capture and this retrogressive erosion process to propagate faster into the upper stream. So this is just to show that even looking only at what happens at the surface processes, there are some known intuitive processes and phenomena that have to be understood. Okay, this is another example where I couple tectonic uplift along this region. This is now tau, so this is a cross-sectional model. And I'm imposing constant uplift rate in this region here. And this constant uplift is being eroded by an amount of constant amount of precipitation. And this leads to the formation of two symmetrical equilibrium river profiles, one in each side of this developing divide. And this we call a steady state formation because the erosion rates that you have here in red, they reach a laterally constant value that perfectly matches the amount of uplift. Okay, so because there is this negative feedback between the generation of topography or relief and the speed at which the surface erosion happens, then this negative feedback leads to this equilibrium in the topography, this topography that becomes steady. This, again, non-intuitively, can also happen even if you make the system much more complicated in a 3D river network. Again, here what I'm showing is this region will be uplifted at a constant rate, but now it's a 3D or pseudo 3D model in which the drainage network has to find the proper drainage pattern that will perfectly compensate this constant uplift rate of this block. So eventually, if a steady state is developing, then the incision rates that you have in the right panel should be also constant and should match perfectly the speed of uplift that is pre-imposed, which is in the order of 0.4 millimeters per year. To even complicate more this setting and test if still the system can develop this steady state, I add orographic precipitation. So in this model, the wind is blowing from the left, and it will face this growing topography in the model, and it will precipitate water in the upwind sides of this evolving topography. And the question is, will it still develop a steady state topography, or is there some sort of positive feedback that impedes the system to find some steady topographic situation that makes the precipitation rates and the erosion rates and the uplift rate compatible with each other? It's really non-intuitive to answer that part. And what happens is that as topography starts growing, you see now the colors, this is the palette for the elevation, and then precipitation rates are, this orographic precipitation is propagating towards the right because the wind is coming from the left. So erosion is propagating towards the right. The drainage divide is also shifting towards the right because of this orographic effect. That breaks the initial symmetry of the system, and eventually you reach this nice equilibrium between the uplift and erosion. And this stops at about 20 million years, and that's why now the topography will start just degrading, lowering down, and flattening the entire relief. Okay, so this was just an example to show that this steady state topography that is difficult to check in the field, in data, but it's a very strong theoretical, let's say, theoretical concept that can be a good starting point to talk about what happens in non-steady state scenarios, which are the normal situations in nature, because you have randomly distributed tectonic faults that are moving here and there. You don't have this uniform uplift situation. So understanding these interplays between surface and deep phenomenon means understanding how and what timescales transient erosion happens. All right, then this will be the first transient experiment I will show. Here we have again a constant block uplifting. This time it's uplifting across an initial equilibrium profile along this initial river. And what you see is that as a consequence of this uplift, you get the formation of a lake. This lake grows until its surface can evaporate all the water that is collected upstream. And this closure of the drainage, this endorrheic system form, is now capturing all the sediment that comes from above. And the fact that the drainage is closing is changing dramatically the delivery of sediment towards the base level or the sea that is next to it. So this is an example of how, and what is controlling the speed at which this lake will reopen and deliver again the sediment to the ocean. That depends on the strength of this block and the speed at which it goes, whether it stops or it goes faster or slower. Another possible interaction is this one. Here now I'm accounting for isostatic response, subsidence in response to the accumulation of sediment. There is no block uplift, but still, because of the erosion of this area here, competing against the accumulation of sediment in upstream, then what you get is a very interesting feedback between what is the isostatic response controlled by the thickness of the lithosphere and the strength of the lithosphere, and the speed at which sediment is passing by these barriers and being delivered to the ocean in this case. So in this model, even if tectonically, in terms of deformation, nothing happens, what is interesting is that the situation in terms of sediment transport is very non-steady. You see, there's this very important slowdown on sediment delivery to the ocean here that is not even controlled by tectonics, but just by isostasy. Okay, so now I will go to the second part, which is about these drainage basins in northern Iberia as an example for what can we learn out of applying this modeling to geological scenarios. Well, welcome to the Duero and Ebro systems in North Iberia. These are two endorheic basins which are very similar to each other. Both are about 85,000 square kilometers in drainage area presently. They are bounded in the north by the Pyrenean, Cantabrian mountain range, and both became closed endorheic systems by the Oligocene. And both seem to have opened by the late Miocene. And yet, in spite of this, all these similarities, the present-day topography seems to be very different. If you look at the scale, this is about 700 meters in elevation, very flat, whereas the Ebro Basin is completely incised and cut down by the river network. So, if you make a cross-section, what you have is this flat elevation here, is very incised in the right basin, which is this is the Ebro and this is the Duero. And this is how it looks like in the Ebro Basin. Again, all these limestones forming during the closed lacustrine period of the Ebro Basin are currently being cut down by the tributaries of the Ebro River. This is a model we did long ago for the Ebro Basin, and I just quickly show it now here to illustrate what you can do with those models. Here you are imposing shortening rates based on structural geology along the Pyrenees and the Iberian Range and the other mountain ranges surrounding the future Ebro Basin, which is eventually captured by one of the streams leading to the Mediterranean, and then is re-incised, reproducing a little bit what I was showing previously. What you have here is Mallorca, the Mallorca Islands departing from northeast Iberia. Let me play it again. And a little bit the conclusion of this article was a bit understanding for the first time that these endorheic deposits in the center of the Ebro Basin, they could be explained actually as the interaction of these tectonic climatic effects that forced the basin to become closed and evaporitic, and the later capture by one of the streams in the Mediterranean capturing the internal drainage of the basin. So and the point of showing that is because we think that the Duero Basin, the neighbor basin to this one, has undergone a very similar evolution, and just with a different timing. And the question is how to make the two evolutions compatible with each other. Why are they so in such a different state of progress, even if they were starting at such similar initial stages. Here again, you can see this is a map of the relief anomaly. So this is highlighting anomalously flat, high elevation areas with low relief. And here you can see very well this problem about the Duero meseta. This is what is very different in the Duero Basin relative to the Ebro Basin. This is what we are trying to understand. It's another way to plot using GIS to plot the same idea, this flatness here at high elevation versus this more equilibrium profile of the Ebro Basin. Well, this would be a scheme summarizing a little bit the idea. Okay? So both basins might have grown accumulated sediment as an endorheic system catched between the surrounding mountain ranges. They overfill, they overtop eventually, and once they overtop, they start being incised. From steepness maps and from, you can see that actually the Ebro Basin is currently capturing or invading along the drainage divide between the two sides. It's invading the Duero Basin. So this is consistent a little bit with higher slopes at the Ebro side, the right side of the Ebro Basin. And this is actually seen in the field, where you can see beheaded rivers like this one that has been very recently. Some people were speculating that this might have happened even in historical times. This river initially going towards the Duero, towards the Duero Basin, is currently being in a very non-equilibrium shape. So this flat topography along the profile is falling at high slope in here. It seems really to have happened really soon. That's the drainage divide. This is the location for this. That's the drainage divide. This is where the capture of this area previously draining towards the Duero seems to now have been captured. All right, now to apply the models, we need quantitative quantifications of the erosion rates in both systems to better understand what happens. So the first thing we did was collecting existing values for the Ebro Basin, and this yields, based on terrace dating, this gives values in the order of 20 to 40 to 80 and 20. Depends where you measure. There is big variability in depending where the terraces are located. Here. And so the same, well, this more examples about the area, but you're probably not so interested in that. So the important point here is that these values become pretty high in some places. In the Ebro Basin, you have up to 500 millimeters per year in terraces that are in the flanks of the basin, not in the central parts. In the Duero, there is less data available, so we had to find new terraces that we could date, and this was done by Laura Rodriguez. She was developing this method for detecting flat surfaces, so we just had to go there, sample them, date them using cosmogenics, and that helped us to have new constraints on what is the speed at which the river network is incising in this area. And this yielded lower values in general relative to the Ebro Basin. These are the ones you have here. They go down to 70 millimeters per 1,000 years near the divide, a bit about double than that in the area we were sampling. And this is in contrast with values that had been obtained previously by Loreto Anton and co-authors that show much higher values along the outlet of the basin. That is the Arribes Gorge, which I regrettably did not bring a picture to show you how it is, but it's really a vertically walled granite rock gorge that is the outlet this this large basin. So, in contrast with the Ebro basin, let's say that this one is presenting a very important variability of the values of incision rates, yeah? From the outlet itself to what happens near the divide, where it becomes slower than the Ebro basin. And this is interesting because it suggests that even though the Ebro is showing the capability of capturing along the drainage divide, is capturing streams from the Duero system, still the Arribes, the outlet of the Duero basin, are incising much faster than the Ebro River is today. And this links with the detection, in this case, performed by our former postdoc, Lucia Struve, in our group, that was detecting a series of different groups of nick points propagating from along the Duero basin at different speeds. Some of them close to the divide, and the main one which would correspond to the Arribes' largest nick point controlling the incision of the entire basin. So the interpretation of this, I will come later to the interpretation, but the idea is that what you can also feel by looking at the chi elevation as a function of chi. Chi is just a way to plot distance along the river. It's a way to plot the river profiles that makes the river become flat when it is in equilibrium. And what you see by comparing the Ebro and the Duero rivers is that actually the Duero seems to be much more in this stage of propagating a very large nick point that is just beginning today to cut through the Duero basin. So this demonstrates that the two basins are actually at a very different stage of incision. The Ebro one is in equilibrium, so it has been eroding already for long, and it has reached a steady situation, whereas the Duero one hasn't yet. And the question is why? And to answer that question, we did this TISC model again. Here are the initial settings, just short after the capture. Topographies are exactly the same on both sides. This just has been already slightly incised because it was overfilling initially. But believe me that the two sides have exactly identical topography. The only difference between the two sides is actually the dimensions of the sedimentary body that is going to be incised, which is slightly smaller in the left, which is the Duero. And what we will see is what we were trying with these models to run it repeatedly to test under what circumstances you obtain this difference between the two sides, preserving the sedimentary infill of the Duero and deeply incising the one in the Ebro. And the results look like this. This is what we were repeating hundreds of times. The results show that because the drainage, the barrier that is separating the Duero basin from the Atlantic is much larger, much wider than the one separating the Ebro from the Mediterranean Sea. Even if both oceans have the same base level, this is what seems to be responsible to produce this finally very well preserved surface of the sedimentary infill of the Duero in contrast with what you see in the Ebro. Let me show again. In the right panel here, you have the incision rates. So you see incision is propagating very fast in the Ebro side, even if the properties of the sediment of the rocks that were in that basin are the same as in the Duero basin. The differences between the erodabilities of this sediment body here and the bedrock of granite imposed in this side and in this barrier of the Ebro basins. Okay, so that seems to be the primary control. There are other parameters we were testing. I will not go into details, but for instance, let me mention the role of elastic thickness. By simply varying what is the thickness of the lithosphere that is supporting isostatically all this mass transport from one domain to the other, you can get a very different response in terms of the time needed for the basin to incise and to reopen. So what we are plotting here is the time needed for starting the incision of the Ebro and the Duero basins, red and black. And you see by just changing the elastic thickness and making it larger, then what happens is that for low values of elastic thickness, you have a more local isostasy in response to erosion and sedimentation. And that kind of makes the river incision block itself as it tries to empty the basin. Just the fact that there is more local isostasy in response to the erosion. So that's what makes that for low values, you have a very delayed time of drainage opening in the Duero relative to larger value. It seems to be like a critical value that makes the whole thing go much faster. So our interpretation of this is what you see in this scheme. The one in the top should also move. Okay, it's just this idea that the Duero basin is going so slow because it has a much harder and wider topographic barrier separating the basin from the Atlantic Ocean. And that allows the system to have two families of nick points that propagate at different speed. One is controlled by the strength of the sedimentary cover. And this is that's the fast trend of nick points propagating towards the divide. And then there is a much slower nick point and much more pronounced nick point, which would correspond to the outlet point. And that is actually controlling this delay in the response of the Duero basin. That's related to the width of the topographic barrier that separates the Duero from the Atlantic Ocean. Okay. 10 more minutes? Sure. Okay, because I will make the link to finish the presentation. I will try to make the link of what I think could improve all this sort of modeling. The limitation of those models, I didn't go much into detail, but one limitation, as I said, is that we have no idea what constants of proportionality between erosion and water discharge are. Those constants, we know they must be related to the lithology and fracturation of the rocks, but there is no table where we can go and say, look, if you have granite, just put this number, or if you have sandstone, put this other number. So these models have very little capability of predicting actually at what speed should drainage evolution have taken place in the past when we want to address a geological scenario. And one idea that we are proposing to obtain some values for those constants is going to outburst flood systems related to the overtopping of large lakes. And this needs a little bit more of explanation. Let's say the problem of why we cannot have good erodibility values from field data is because we have very poor knowledge on what were the past conditions of climatic conditions. How much water was going down a river when it produced the incision rate that we measure in river terraces or so on. That's the real problem we have. We know at what speed the erosion goes, thanks to these cosmogenic patterns and etc. But we don't know how much water was produced in that. So that's limiting our discussion about, obtaining good, precise erodibility values for our models. In this scenario, we think this could be the right place to measure those Ks, to measure those constants, because they have intrinsically well-known hydrological conditions, and I will show why. Didn't mention this picture is from perhaps the most well-known case of lake overtopping on Earth. This was first described by Gilbert in the 19th century. He was brave enough to suggest that these rounded boulders might have been caused by unprecedented large mega flood, as we know them today, related to the overtopping of Lake Bonneville. He didn't study that further because at that time talking about mega floods was heretical for geologists. It was forbidden. It was about the fight between catastrophism and scientific geologists. So, but then it was studied again during the middle and late 20th century, and today we know a lot about this mega flood that involved around 1 million cubic meters per second of discharge, capable therefore of moving these up to 10-meter wide boulders and make them round along the pathway. This is a common phenomenon in nature. So here you have, for instance, this moraine lake that in 1984 it was overtopped and then catastrophically discharged, and well, it caused some trouble downstream from here. And this is an example from 2010, where the same happened from a landslide was blocking a river, and this formed a lake behind that did not exist before, and in a matter of a few months, the lake started overtopping, and all this river in Pakistan had to be evacuated, and then, which is very costly, of course, but nothing happened. The lake started flowing like that calmly, and there was no catastrophic outburst flood out of this overtopping. So this is just to show that today there is no good approach to predict what the risk out of these systems of overtopping lakes are, which is another reason why studying these systems is interesting. Well, the models we did are very simple. They are just a 0D model is focused on what happens in the outlet, and it studies the feedback between how much water can go through the outlet and at what speed it incises into the and how the growth of due to the growth of the outlet due to seal erosion is feeding back with the amount of water that can get out of that lake. And this is a video. Let's see if there is a quick video to show what the system, this phenomenon happens. You see, same as I said, that it's very difficult to assess what is the dangers of or the risk related to overtopping lakes. You can feel that limitation yourself, because if you try to imagine how big will this overtopping flood develop, it is very non-intuitive. It's very difficult to think. Even if I tell you how big this lake behind is, it's about 20 square meters. This is compacted sand. It is difficult to think how fast will this flood become before the lake becomes empty and there is no risk anymore, right? So in this experiment, I'm just skipping a few seconds from time to time. It lasts actually about 5 minutes. But in this experiment, you will see that the erosion along the sill you can see from behind this camera. This camera is placed in the lake around there. And here you can see where is the water actually coming out of the lake. So, and it's dragging these pebbles, or this rubble and the sand is grabbing them and dragging them and making an ever-increasing shape of an ever-increasing depth and size of this outlet of the lake. eventually leading to very large water discharge, as you can see in this later stage. So it is very non-intuitive to imagine how big will the event come. In the field, geomorphologists, experienced geomorphologists like John Jansen can go to the field and they can see features like these, which are run-ups. This comes from the Altai mountains where such an outburst flood has been found. So imagine this is very recent, this is Pleistocene. So essentially this valley was the same when the flood occurred. And this means that water came up to here. This is more than 120 meters above the channel elevation. So this means that the flooding waters were going up to this elevation and were dropping these materials that you see, these flat materials that you see here, which are gravel-sized, rounded sediment that was deposited during the high stand of these flooding waters. And this gives very good hints as to how high the waters were and what was the amount of water that was coming down that river. So I could not stop myself from showing you an image of the device we have for outreach in our lab, trying to show this type of, to teach this type of phenomenon. This is an augmented reality sandbox device where we can play with the sand. And this is kind of reproducing such flooding coming out of a closed lake. And you see, we are plotting the energy of the water in colors, and green means low energy. So that would, these green values you can see over there, that would correspond to the place where these run-up deposits are accumulated during the breaching of basins like that. Sorry, I'm going a bit fast on this. I don't want to bore you, and we should be ending soon. Okay, all I wanted to say is, well, you can model numerically all these phenomena. You can take data like this. This comes from the experiment that you saw in the video. So this is the evolution of water discharge fitting with the results from the model. So these are measurements fitting model results. The same for the Bonneville flooding. Note that there is 7 orders of magnitude in difference in area between these two systems. This is the sand experiment you saw in the video and the Lake Bonneville. And still the model is capable of accounting pretty well for the two evolutions. And what the outcome of this modeling gives, the parameter with which you play to fit those values are these Ks, are these erodibilities. So these values that we take here and here, you see this value is very small, 4 orders of magnitude smaller than this one here, which is consistent, let's say, a priori, with the difference between what the outlet erodibility is in both systems. It was compacted sand here and consolidated fluvial deposits in the Bonneville basin. So it seems like this type of modeling can give us erodibility values, and that's why we then plotted the results from these outburst plots here in blue, and we compared them with pre-existing erodibility estimations coming from landscape evolution models, the ones in red, and we see some consistency between the two, and that's why we were very happy with these results. We published in scientific reports a couple of years, 4 years ago already. And because we think that this consistency between the magnitude of these erodibilities for very strong lithologies and the values we obtain for overtopping lakes based on geomorphological studies of the discharge along the outlets of overtopping lakes, they seem to have some sort of consistency between each other. So maybe the good controls that we have on overtopping lakes, outburst floods are a key to provide us more reliable values for the erodibilities needed for modeling geological scenarios. I think I will leave it here, and I'm open to your questions. I hope it was not too long. Sorry.
Well, thank you very much, Daniel, for a brilliant talk, and I'm sure there will be all kinds of questions from the audience. John, maybe? Yes.
Yeah, thanks, Daniel. This is really interesting synthesis of much of your excellent work. With the erodibility indices that you've been exploring, I suppose you're looking at homogeneous erodibility. How much more complicated does it get when we start to find, which we do find in some of these dams, enormous blocks interspersed with smaller fine-grained materials? So we have a mixture of erodibility. And how does that affect the sums?
Yeah, this is actually, I was discussing this with Greg last week, that this would be a fundamental step forward. I think that someone should do, I hope we do, implementing more detailed models for grain size dependent removal of blocks from these outlets in overtopping lakes. And I'm talking of the outburst flooding model. I guess you are also interested in that, more than in the geological scale, because that would be, let's say, too little information about what happened in the past. But in the case of outburst floods, definitely it would be very important to, instead of using this homogeneous erodibility I was using here, having a more realistic data-based distribution of grain size of these boulders or rocks or gravels blocking the outlet of the lake. And that should need some direct measurement, I guess, to have a population of what is the grain size that is blocking that lake. And then implementing a quantitative way in which the erosion model is not simply applying a constant erodibility for everything, but is dragging one by one grains or statistically in some sort of a statistic way, grabbing material at a speed that depends on that grain size that you are talking about. So yes, yeah, this is, if we have that, my suspicion is that we may have something fundamentally better for predicting the peak discharges that one should expect from the other overtopping of a specific lake that is overtopping. Yeah. We could improve the risk assessment, let's say.
Thank you. Yes, Greg.
Thanks for the great talk, Daniel. I was wondering if you had thought about, probably you have thought about incorporating like a stochastic uplift function in a landscape evolution model, and what you think that might, the effect that might have on the final form of the landscape. Like you showed the steady state, you can achieve steady state, but if you were to include like a stochastic function where the mean is the same as like what you would have in a constant uplift scenario. But, do you think that would affect
you mean
final, the final, well, do you think that could induce kind of a constant transient within the model? Or also if that could affect, you know, the timing of capture, if you have a sill that's being uplifted but not at a constant rate, if that would affect the timing of capture of an basin.
Yeah, well, not your point is makes completely sense, of course, because we know the data I was showing from the Ebro Basin, for instance, is already showing. If you look at the age of the terraces, that incision rate is not regular at all. We don't even know very well what it depends on. And those terraces themselves, they are produced by glacial, interglacial periods that that is already in itself is showing that climate variability or let's say this, that the episodicity of the water discharge, whatever the sources, climate regular changes or just shorter term climate changes, that is crucially determining the formation of these terraces, the speed at which this river incision takes place. Of course, all that is in these teeth models everything is put down into this stream power law approach. And there are already existing better models that already exist, that have been tested, and that you can implement that. The question is whether you have enough data to constrain the behavior of such an increasingly complex model, in which you have more and more parameters. For instance, do we know what these stochastic variations or these episodic changes in water discharge or in precipitation, for instance? Do we know what the spectrum of these episodes was in the Pleistocene or in the Neogene? You need something to fit the model that you can more or less be confident of. No? But as a theoretical exercise, definitely, it would be definitely interesting. Yeah. So there are so many things to do, but this is one of the most important ones, definitely, yes.
Thank you. Sergio, you had a question?
It was almost the same question, basically. You are talking that there is some variation temporarily in the water content, water river. And maybe there was also some lateral variations. One basin and the other one may not have the same amount of rainfall.
You're talking of the landscape evolution models?
Yes.
Yeah, in almost everything that you have seen here.
The constants.
Except, well, I showed this orographic precipitation, that's different, but in the rest, usually, because we don't know with any detail what was the precipitation distribution in the Neogene, in Iberia, or anyone. No, usually the hints you have on that are or yes, exactly. Or for instance, well, in that old Ebro basin model I was showing the animation with the tectonics and so on, that one, for instance, is accounting, for instance, for a low, a relationship, a proportional relationship between precipitation and elevation. And I wanted to do that because if I was not doing that, then I was eroding, I was getting too low erosion in the highlands, in the Pyrenees. So in this case, I needed to put some exaggeration of or some extra precipitation in the higher areas than in the basin, in the lower basins. But yeah, we could have done that, probably changing also erodibilities within the immense range of uncertainty that we have on those values. So again, you see, you can add more and more things, but it will not learn you anything of your geological scenario unless you have very good data to fit the model, to constrain the model evolution. Yeah.
Thank you. There's a question in the online chat, so let me just read it aloud from Luca Malatesta. Excellent talk, thank you. A question about the Duero Basin, evaporation and orography. You showed the role of orography and of infiltration or evaporation at the beginning of the talk. How do these factors influence the dynamics between the Ebro and the Duero? He was unable to unmute himself, so that's why.
So I don't know if I understand the question. The question is how precipitation and evaporation, the equilibrium,
how do these factors influence the dynamics between the Ebro and the Duero?
The underlying assumption on my models is that climatic conditions were very similar between the two basins. But we really don't have, let's put it that way, that I know there is no reason to think that there was different climatic conditions between the Ebro and the Duero at the same time. And this is the underlying assumption to our modeling results. That's why we focused on what was the role of these topographic barriers, different sizes of topographic barriers for one basin and for the other.
The moisture sources are still from the west, aren't they? So there's nothing blocking each.
Yeah, it comes from the northwest. Yeah, but let's say the precipitation patterns in both sides are not dramatically different because both have the northern flank, which is the Pyrenean Cantabrian mountain range that is blocking from the orographic precipitation coming from the Atlantic. So they are relatively dry basins, which anyway, we know it was like that in the Neogene because otherwise you would not have endorheic systems. And this is clearly reflected in the sedimentary record, which is evaporitic. You have these evaporites all over the two systems. So it had to be a dry climatic system similar to today's. So if nowadays you would close the Ebro or the Duero basins, both would become endorheic because they receive much less water than what would be needed to overtop in their surroundings. So,
is Luca happy with that?
Oh yeah, obviously, yeah. Luca writes he's happy, and we can move to another question.
Thanks, Luca, for the question, wherever you are. May Luca be happy with the answer.
Okay, so I believe we have reached the end, I guess, of the indoors part of the event. But let me before I say thanks for the last time, make two brief statements. One is that Daniel will be giving another talk about his work, about different topics in exactly 1 month from now. Actually, it'll be a Wednesday, but the 16th of March at the Faculty of Science of Charles University here in Prague. And he'll be talking about modeling the Messinian salinity crisis and associated catastrophic events in the Mediterranean. So I hope that this will be also of great interest for many of you. And it will also be in a hybrid format. So it'll be both at Charles University and online, and you will receive, and we will advertise the appropriate links in due course. And the second announcement is that those of you who would like to continue discussions or just chat with Daniel in a less formal way than here, in about 15 minutes from now, we have booking of several tables at the restaurant Ubřízy. Oh, short walk from here. So I didn't know. Invited. Apologies to the online folks. That's the disadvantage of being only online. But we are very happy that you have joined us. And thanks, Daniel, again, and thank you all for coming. Or
thank you. I will still be here for quite some time. So
yeah. Okay.